On June 10, 2000, London opened a bridge designed to celebrate the beginning of a new millennium. Within minutes, people crossing it noticed something disturbing. The bridge was moving sideways beneath their feet. At first, the motion was small. Then the crowd grew. The movement became stronger. People widened their steps, reached for the handrails, and struggled to walk in a straight line. London's elegant new landmark had started wobbling on its opening day. The Millennium Bridge crossed the River Thames between St. Paul's Cathedral and Tate Modern. It was the first new pedestrian bridge across the Thames in central London for more than a century. The project had been selected through an international competition. The winning team brought together architect Norman Foster, sculptor Anthony Caro, and engineers from Arup. Their design was deliberately thin and restrained. Most suspension bridges placed their cables high above the deck. The Millennium Bridge placed its main cables low, beside and below the walking surface. The result was a shallow suspension bridge that appeared almost like a blade of light stretching across the river. It was more than 300 meters long. Its central span stretched 144 meters between the river piers. The suspension cables sagged only around 2.3 meters, creating the bridge's distinctive low profile. The design had been carefully studied. Engineers analyzed its structure, tested wind effects, and modeled how the bridge would respond to normal loads. The bridge was strong enough to carry the people crossing it. The problem was not that the structure was about to break. The problem was movement. On opening day, tens of thousands of people arrived. At certain moments, as many as 2,000 pedestrians were on the bridge. The crowd created forces that were different from the loads engineers had traditionally focused on. A person does not walk in a perfectly straight line. Every step moves the body slightly from side to side. Normally, those tiny sideways forces are random. One person leans left while another leans right, and the movements largely cancel each other. But the Millennium Bridge was exceptionally light and had very little natural damping. Damping is the ability of a structure to absorb movement and prevent it from continuing. A heavy, highly damped bridge quickly removes energy from a small vibration. A light structure with low damping can allow that motion to grow. As people crossed the Millennium Bridge, their footsteps created a small sideways movement. Once the bridge began moving, pedestrians instinctively adjusted their steps to remain balanced. If the deck moved left, people shifted their weight. When it moved right, they adjusted again. Those reactions added more energy to the bridge's motion. The bridge influenced the pedestrians. The pedestrians influenced the bridge. A feedback loop had begun. The movement was not a dramatic up and down bounce. It was a slow sideways sway. Video from the opening day shows people walking with unusually wide steps, some holding the railings and others stopping altogether. Measurements and later analysis found lateral movement of up to approximately 70 millimeters in the central span. 7 centimeters may not sound enormous, but under a person's feet, on a crowded bridge above a river, it was more than enough to destroy confidence and make walking difficult. Officials attempted to limit the number of people crossing, but the bridge continued to move. 2 days after opening on June 12th, it was closed to the public. London had just opened its new landmark. Now barriers blocked both entrances. The press immediately gave it a name that would survive for decades: the Wobbly Bridge. The closure was embarrassing, but the engineering challenge was deeper than simply making the structure stronger. The bridge was not failing under its weight. Its components were not cracking because they were too weak. Making the entire bridge much stiffer would have required major structural changes and could have destroyed the elegant appearance that made the design special. Engineers first needed to understand exactly how a crowd could create such large lateral motion. Tests began using instrumented sections of the bridge. Groups of pedestrians walked across while sensors recorded forces, acceleration, frequency, and movement. Researchers also tested people on moving platforms to understand how the human body reacts when the floor beneath it begins shifting sideways. The phenomenon became known as synchronous lateral excitation. The traditional explanation is that the bridge begins moving slightly, causing pedestrians to adjust their gait. As more people respond to the same movement, their sideways forces become increasingly coordinated. That coordination strengthens the vibration. It resembles soldiers marching in step, but sideways, and without anyone consciously choosing to synchronize. The effect had been observed on other pedestrian bridges, but before the Millennium Bridge opened, it was not fully covered by the design rules normally used for a bridge of this type. The bridge had passed the calculations engineers were expected to perform. The crowd revealed a behavior those calculations had not captured. Later research added an important complication. The simple story says the pedestrians first synchronized with one another and then caused the wobble. More recent analysis suggests that perfect crowd synchronization may not be necessary to start the instability. Even pedestrians whose steps are not coordinated can, on average, feed energy into a moving bridge. The bridge motion can begin first. The visible synchronization of the crowd may then become a consequence of the wobble rather than its original cause. The precise mathematics are complex, but the practical lesson is simple. A structure carrying people is not interacting with passive weight. People feel the structure move. They react, and their reaction changes the forces acting on the structure. Once engineers understood the feedback loop, they faced two broad options. They could redesign the bridge to make it dramatically stiffer, or they could add systems that absorbed the unwanted motion. They chose damping. Under the bridge deck, engineers installed 37 viscous dampers. These function in a similar way to large shock absorbers. When parts of the bridge move relative to one another, fluid inside the devices resists that movement and converts some of its energy into heat. But viscous dampers alone could not control every important vibration mode. Engineers also installed tuned mass absorbers beneath the deck. A tuned mass is a carefully designed weight connected to springs and damping elements. When the bridge moves in one direction, the tuned mass moves in a way that produces a counteracting force. 4 pairs were designed to act against lateral movement in the central span. 26 additional pairs were installed to control possible vertical vibrations. The devices had to fit beneath the deck without ruining the bridge's clean appearance. Many of them remain almost invisible to the people walking above. The repair was not simply a matter of attaching a few shock absorbers. The dampers needed to work with movements measured in fractions of a millimeter. Their locations had to make use of tiny relative motions inside the structure. Engineers developed special A-shaped frames beneath the deck to amplify those movements, enough for the dampers to work effectively. The solution transformed the dynamic behavior of the bridge without transforming its appearance. But calculations alone were no longer enough. After the embarrassment of opening day, the bridge's owners wanted direct proof that the modifications worked under a full crowd. On a January evening in 2002, approximately 2,000 people gathered for a large-scale test. They crossed from the south bank to the north. Then they regrouped and walked back. Sensors covered the bridge. Engineers watched the vibration measurements as the crowd moved across. This time, the uncontrolled sideways motion did not return. The added dampers and absorbers were working. In early 2002, almost 2 years after its original opening, the Millennium Bridge reopened to the public. Since then, millions of people have crossed it safely. The nickname remained. The wobble did not. The Millennium Bridge is sometimes described as a simple engineering failure. But that description misses what makes the story important. The bridge was structurally strong. Its designers performed extensive analysis using the knowledge and standards available at the time. What opening day revealed was a missing interaction between a structure and the humans using it. The people were not just passengers. Their attempts to remain balanced became part of the bridge's dynamic system. The failure also produced something valuable. The research that followed changed how pedestrian bridges are analyzed. Designers became far more aware of lateral crowd-induced vibration and the need to consider human reactions to structural motion. Today, the Millennium Bridge remains one of London's most recognizable modern structures. Its slender profile still points directly toward the dome of St. Paul's Cathedral. Most people crossing it never see the dampers beneath their feet. They do not notice the tuned masses, the A-frames, or the devices quietly absorbing movement. The solution is hidden inside the bridge, and that may be the best ending an engineering failure can have. The structure remained, the lesson was learned, and the problem disappeared beneath the blueprint. Subscribe for more engineering failures, expensive mistakes, and hidden systems shaping our world.